Okay. What's happening here with the integrating factor? If I were to give you an ODE and you write it in this specific form, so if an ODE can be written in this form, plus p of xy is equals to q of x. So if an ODE can be written in this form, and you can make it be in this form, right? So if in this case I had maybe x, for example, right, I could divide throughout by x to make sure that I have a function of y being the coefficient of y, and dy dx not having any coefficient over here. So if a function can be expressed in this specific form, we can do very interesting properties. So if you have a function like this or other similar functions or other families of functions like this, you can do very, very cool things. So let's assume a function I was to exist, okay? So let I of x be a function that could exist, right? So I'm going to call this the integrating function, or the integrating factor, if you will. So if I were to have a function I of x such that if I multiply throughout, so if I say I of x dy over dx, and then I of x p of x, y is equals to I of x q of x. If I were to have this function I of x, that if I multiply, I didn't do anything tricky, I just took I of x and I multiplied it throughout. If I were to have this function such that if I multiply throughout everything with that specific function, I have this property over here. If I were to do this and say dy over dx of this specific thing, so if you have y, basically its derivative is dy dx, and if you have I of x, its derivative is I of x p of x. So I of x p of x, you can basically proceed to obtain the solution that we normally do, and then you can proceed to do this, and then you can proceed to do this as well. Okay, then after that, so y I of x is basically equal to the integral of I of x q of x dx. So what you're doing here is proving that if a function I of x was to exist such that, so if a function I of x was to exist, okay, if a function I of x was to exist such that, okay, such that the derivative of I of x was equal to the product of I of x times p of x. So if a function was to exist such that this was possible, then this would exist. Then this would exist, and that would be good. Okay, so we want to find a function such that its derivative is equal to this specific thing. Okay, it's very easy to find the value of I of x because we can realize some very, very important cool things here. So you can realize that if you want this to be true, basically I prime of x over I of x can be equal to p of x. So you can basically divide on this specific side over here. And if you're to integrate both sides with respect to x, so integrate both sides with respect to x, integrate both sides with respect to x. Okay, if you're to integrate this with respect to x, you can realize that the integral of the derivative of a function divided by that exact function. So if I were to find the derivative of 2 over x squared, so 2x over x squared, for example, you can realize that if the numerator, so it's called integration by recognition. So if you realize that the numerator is the derivative of the denominator, you can basically write the ln of the numerator, of the denominator, sorry. You can basically write the ln of the denominator. So we can realize that the numerator is a derivative and the denominator is I of x. So it's very easy and straightforward to realize that, wait, the ln of I of x is basically equal to the integral of p of x dx. So we can now easily confirm that if we were to introduce e on both sides, so e to the power of ln I of x, that's going to be equal to e the integral p of x dx, right? We can easily prove now that I of x is equivalent to the e function in this specific form. Okay, and this is fun. Like, this is really important because we've just found an integrating factor. It's basically the function such that if you're to multiply it throughout, you can basically do all those cool things. And you can easily see this because remember, I started off by saying if I have a function like this plus p of x multiplied by y is equal to q of x. If you now multiply throughout by I of x, so basically if you were to multiply throughout by I of x, okay, you can realize that if I of x is equals to e, the integral of p of x d of x, okay, multiplied by dy dx, plus e, the integral of p of x dx, multiplied by p of x y, is equals to q of x e, the integral of p of x dx. You can realize that the derivative of y is effectively dy, that's good, and the derivative of this, or expression over here, is basically you drop the power. So to find the derivative, you basically differentiate this specific expression. And remember, the derivative of an integral is basically the same function, right? To reverse integration by differentiating, you get the exact same thing. So that's what you multiply by. So if you have maybe e to the power of x, right, or 2x, you first find the derivative of this, which is 2, then you multiply by that derivative, right? So in this case, we have e to the power of p of x dx, and you multiply by the derivative of this guy, which is just p of x. And you can see that this is the exact same derivative of this guy that is over here. So that's good. So what that means is that basically d over dx of y e, the integral of p of x d of x, is basically equal to q of x e, the integral of p of x d of x, which is good because now you can basically find the value of y, integrate both sides with respect to x, and then you can be able to obtain the value of y effectively, right? Because if you integrate both sides with respect to x, so this is with respect to x, and this is with respect to x, you can basically obtain the value for y, which will be an expression that we can find. So basically, this is what we call the integrating factor. It's basically an equation that you multiply throughout by to convert any ODE and linear ODE in this form to an exact differential that you can easily solve by utilizing these principles that we introduced when first talked about exact differentials. So you might be wondering, how is this useful? Can we have an example, please, applying this? So that's what I'm going to do, and that'll be the last thing in our video. Really be sure that you've understood this concept like thoroughly. So I can give you this example, right? And I want to give you a complicated example so that you can be able to hone in and understand these concepts. So it's important for you to realize that if you have this specific thing, you've realized that you can't do anything, you can't separate y. When all hope has failed, you can introduce an integrating factor because you realize that, wait, this matches the form that I've learned, right? This basically matches this form that I've learned, okay? So that's good. So you can first start by just saying, let p of x be equal to tan of x, and let q of x be equal to sec of x. Okay, so you know that your integrating factor is basically e, the integral of p of x dx. This is something that you should just know and memorize. Like, as time goes on, you get used to this specific fact that this is what the integrating factor actually is. So you know that this is true. So basically, e is the integral of p of x, which is tan x, the integral of tan x dx. Okay, So you're not necessarily expected to like know the integral of tan of x. You can derive it, but for most of these questions, if you're, for example, doing engineering, you're given a booklet that contains all the derivatives that you need so that you don't have to do it multiple times. So I know for a fact that the integral of tan x, so I don't have to keep on doing that, is basically negative ln cos x, right? So I just know that this is true, right? That the derivative or the integral of tan of x is basically negative ln of cos x. And that's very, very good, right? Because I can substitute that and have e to the power of negative ln cos x, right? So I can realize this is e to some ln function. So I can make this easier for myself and just say that this is e ln cos x to the power of negative 1. Remember, ln cos to the power of negative 1 is 1 over cos x, right? Which is basically sec x. So e 1 over cos x is basically sec x. Okay, so we have e is equal to the power of ln sec x. So that means this answer that I'm going to have here is basically going to be sec x. Okay, so sec x is basically going to be my integrating factor, I of x. So this whole process is what you go first through, right? Defining an integrating factor and undergoing all these processes to be able to integrate it and just have the integrating factor at hand. So what this means is you're going to multiply this equation throughout by your integrating factor. So you're going to have sec x dy over dx plus tan x sec x y be equal to sec squared x, because you multiplied this sec x by sec squared. Okay. And using your book again, so you're not really supposed to know this by head, but the integral of sec x, or the derivative of sec x rather, the derivative of sec x is basically tan x sec x. So that's good because the derivative of y is dy dx. So we can basically then say that d over dx of sec x y is equal to sec squared x. Okay, and that's pretty good. So the process that follows is basically doing this, and you basically will be done. So if you do that, the integral of sec x of sec squared x, and if you do that, you basically have sec x y. The integral of sec squared is basically tan x. Again, you have a data booklet or a list of formulas, so you can be able to see that this is true. Okay, so now we're done. So y is basically equal to tan x over sec x plus c over sec x. And you know that sec is 1 over cos. If you want to be fancy, you can just divide by 1 over cos. This gives you tan x cos x plus c cos x. Okay, so this is what we call an integrating factor. It's basically this specific equation with this specific form that you're able to utilize when you see an ODE that can be expressed in this specific form. So there are a lot of ways, a lot of examples that you can try to better understand and solidify this concept. You can easily Google and look for questions online where you are utilizing this concept and you practice it a lot on different questions.